One of the reasons that we study probability in geometry is so that we can study geometric probability, and it always falls after area because it has to do with the space and how does the space where I want to land compared to the space where I can land. So the way that it looks is the number of outcomes in the event and the number of outcomes in the sample space. Again, this comes back to what I want to happen or how much space is where I want to land versus how much where I can land. So we have on this table several different situations. So say we have a number line. And I want to know, kind of like pin the tail on the donkey, I want to land in any one of these spaces. I want to land on this number line. I want to land in this circle in that area, that angle measure, or I want to land inside that triangle on that rectangle. So think pin the tail on the donkey. So what if it's a number line? Well, where I want to land is on BC. Where I can land is anywhere on AD. So I would put the length of BC divided by the length of AD, and that would give me that probability. Well, what that looks like is this one right here. So I want to land on AE. So here is AE. AE is 1, 2, 3, 4, 5, 6, 7, 8 units long. So that's where I can land. I can land anywhere from A to E. I want to land on CD. Well, CD is right here, and it is 1, 2, 3 jumps. So I want to land, I have a space of 3 where I can land, where I want to land. I have a space of 8 where I can land. And so the fractional probability that I would land somewhere on AE within CD is 3 out of 8, which your percentage probability would be 37.5%. Then we have our angle measures. So angle measures are the easiest because it's 360 degrees total. So you just do the angle where you want to land divided by the 360 degrees. So if we look at this problem, this example 2, I want to land in red. So I look at red. Red is 45 degrees. Well, 45 degrees out of 360 degrees is my probability. Now we always reduce it. That is 1/8 of the circle. 45 divided by 360 is 1/8, which is 0.125 or 12.5%. What's the probability of it landing on purple or blue? Remember, this is where we add them together. I don't care whether I land on purple or blue. So if I take purple and blue and add them together, that's 135. So 135 divided by 360. Okay, if you divide that, say I asked for it in percent probability, you would get 0.375 or 37.5%. So we have a 37.5% chance of landing in those two places. Okay, so how about the probability of not landing on yellow? Well, if I don't land on yellow, then I land anywhere else on green or red or blue or purple. All of those make me happy. Well, that's 260 degrees that makes me happy out of the 360 degrees that exists. So when I divide that, 260 divided by 360 is 72.2% if I convert it to a percent probability. Okay, so this last one is area. So I can land anywhere in this rectangle. If you look here, I can land anywhere in the rectangle. Think of it like a bulletin board or a board at a carnival. I want to land in the triangle. And so you would do the area of the triangle divided by the area of the rectangle. Okay, so it's the small space where you want to land divided by the big space where you can land. So let's look at a couple situations here with these problems. So find the probability chosen at random. So we have a dartboard, and it looks like this with a white rectangle and a black rectangle. So the first thing is I want to land inside the white rectangle. So what I need is the probability of the area, the white area, over the black area, which would be the whole big area. Okay, I say the black area. I don't want to be that specific yet. I want the whole area, which the whole area is I can land anywhere in this bulletin board, but I want to land inside this white space. So the area of the white space, it's a rectangle. 4 times 8 is 32. So it would be 32 divided by the big rectangle, which is 6 by 10, which would be 60. Okay, 32 over 60 reduces to 8 over 15 as a reduced fraction, or 53.3%. So a 53.3% chance of landing in the white area. Now, what if I want to land in the shaded area? Okay, so what I want is I want to do shaded over whole. Well, that means I need to find the shaded area. Well, the shaded area is the 60, right? So let's take a step over here and try to figure this out. So the shaded area is 60. The white area is 32, and it's a whole, so I'm going to subtract it. That 32 is inside that black one. So 60 minus 32 is 28. So I have 28 square whatever, inches, feet, whatever, of space where I want to be. So I want to be in that 28, but I can be in the whole 60. I can be anywhere in that whole 60. So 28 over 60 reduces to 7 over 15. And if you take that and convert 7 divided by 15 and change it into a percent, you would get 46.7%. Okay, then this last one, darts. So we have a dart game. It uses a target with concentric circles. That means they all have the same size. The first one has a radius of 5. The medium-sized circle has a radius of 8, and this bigger outside circle has a radius of 12. So think of it as 3 separate circles. We have our radius of 5, we have our radius of 8, and we have our radius of 12. That's what we have. Okay, so what's the probability that I'm going to land in the spot of 20 points? Well, pi r squared. Right, if I pi r squared each of these, I'm just going to leave them in terms of pi just so I don't have to deal with decimals, okay? So 8 squared is 64, 12 squared is 144, and I'm going to leave it in terms of pi. It'll take care of itself in a minute. So the area where I want to land, which is 20 points, is 25 pi. The area where I can land is in the whole circle, assuming that we're going to land on the dartboard. Okay, so we're gonna assume that we're gonna land on the dartboard, and that's what it means by it's equally likely to land on any point of the target. It means you're not gonna miss the target. So, but the whole dartboard is 144. So there's 144 square inches where I can land, but there's 25 pi square inches where I want to land. Well, this is why I left those pi's, because look what happens. Those cancel out. So 25 over 144 is, if you put that in percentage, change that to a color you can see. Why won't it change? There we go. Is 17.4%. Now, what's the probability of it landing in the 15? Well, notice that the 15 has a hole in the middle of it, right? So here's the tricky part. This is where we want to land, is right here. So what we want to do is, we have a couple of options. You can take the big circle and subtract the little circle. You can take the medium-sized circle and subtract the little circle. In the end, it doesn't matter. You're going to get the same amount of space. Okay, so let's take that, let's take the 64, right? Let's take that 64. I want to land in the 64, but I want to take away the 25 because I don't want to land in that space. So 64 minus 25 pi is 39 pi. So I want to land in that 39 pi. I can land in that 144. So I'm going to land there, and I can land anywhere in that 144. So my pi's cancel out. So 39 divided by 144, and you get 27.1%. Okay, and so you have to find, it's the area of what you want, the length of what you want, the angle measure that you want, divided by the length of where you can land, the 360 is the whole degrees of the circle, or the area of the entire shape where you can land. It's still where you want to be, or what makes you happy divided by what all can happen. That's still how you calculate